This next lecture is called Standard Heats of Formation. Let's say, for instance, you had this reaction. 2CO2 plus O2 yields 2CO2, and you wanted to know what that delta H value was. Well, you would say, okay, just give me a couple of reactions to manipulate, add them up, so that I can find the delta H for that, using Hess's law, and that would work. Except, what if you didn't have Hess's law? What if all you had was this table? Well, it turns out that this table is more than sufficient to find delta H without using Hess's law. In fact, you could solve all of these equations. You could find their delta H values using nothing but this table right here. And we're going to learn how we do that. So, introducing standard heat of formation, which is represented by this symbol here. So, delta H, that's your heat change. That should be pretty obvious. Formation is represented by that F, and that symbol there represents standard conditions. Now, in terms of enthalpy, standard conditions means 25 degrees Celsius or 298 Kelvin, and it also means 1 atmosphere. So, any other conditions would not be considered standard conditions in terms of standard enthalpy. So, this is the way it's used. If you wanted to find the standard heat of formation of, say, ethylene, which is represented by C2H2, and that's a gas at 25 degrees Celsius. Well, from this, we will already know the equation because, by definition, standard heat of formation is equal to the amount of energy in kilojoules required to form 1 mole of a substance from its constituent elements in their elemental state at standard conditions. So what that means is the reaction we're considering is the formation of C2H2 gas, which means that's the product, from its elemental constituents. Well, the elements that make it up are carbon and hydrogen. Now, in their elemental state, carbon is solid and hydrogen is diatomic, and it is gas. And of course, it needs to be balanced, so the coefficients will be 2, 1, 1. There are textbooks dedicated to providing the standard heat of formation of thousands and thousands and thousands of substances. So if you looked up C2H2, its value would be positive 224 kilojoules per mole. So it turns out that if we look at this table right here, let's pick one. Let's pick methane, right? Well, to form methane, right, your elemental constituents are carbon and hydrogen, CH4, gas, right? And we have to balance it, so it's 1, 2, 1. Well, the delta H for this reaction, the heat of formation at 25 degrees Celsius, is equal to negative 74.8 kilojoules per mole. Now I want to address a special case, something like this one. Let's say we wanted to do HCl. Well, the standard enthalpy of formation for HCl gas is negative 92.3 kilojoules per mole. So the reaction would look something like this. To form HCl gas from its elements, which are hydrogen and chlorine, well, we would put H2, because hydrogen is diatomic and a gas at room temperature, plus, and we would put Cl2, because chlorine is diatomic and a gas at room temperature. Now, if we tried to balance it, we would get the coefficients of 1, 1, 2. Now, what you have to remember is the units for the standard enthalpy of formation is kilojoules per mole. So this energy value does not reflect that reaction. It only reflects a reaction where the coefficient of HCl is 1. So, what do? Very good, you guessed it. Cut everything in half. the coefficients are actually going to be 1/2, 1/2, and 1. Yes, fractions for coefficients are now allowed. So the standard heat of formation for HCl gas is negative 92.3 kilojoules per mole, and this is the reaction that it's representing. Alright, now get ready for a scary looking equation. Believe it or not, this is not the scary equation, this is just real quick to tell you. Here are the reactants, we're just using arbitrary letters to represent the reactant side, and here are the products. So the uppercase are representing the substances, and the lowercase are representing the coefficients. Alright, here's the scary equation. So you can find the heat of any reaction, the enthalpy change of any reaction at standard conditions using this equation. Don't get fooled or don't get scared by this, it's very simple. That symbol just means the sum, adding everything up. The letter N and the letter M represent the number of moles, more specifically your respective coefficients of each of your substances. You know what the delta H values are, you're going to get that from your tables, and basically the main idea is that it's always products minus reactants. Now we're going to rewrite this equation to something else that might be a little bit easier for you to understand, even if it looks a little more complex. Alright, so don't be too overwhelmed here. So, the main thing to remember is this. Your heat of reaction is always going to be products minus reactants. So, to find the heat of any reaction, if we know all the standard heats of formation of all the substances, we can calculate it, and it's very simple. You're going to do the product side first. You're going to multiply the coefficient of a product times the standard heat of formation of that substance. So C times the standard heat of formation of substance C plus, and you're going to add up all the products. So it's going to be plus the coefficient D times the standard heat of formation of that substance D. And if there was another product, it would be plus E times standard heat of formation of E, plus however many products there are, it's its coefficient times the standard heat of formation of that substance. And then it's going to be a big old minus, and then you're going to do the same thing with all the reactants. You're going to add up all the reactants. So A, the little lowercase a, is your coefficient, times the standard heat of formation of substance A, plus B times the standard heat of formation of substance B, and you would do it with as many reactants as there are. So just kind of let that sink in for a moment while I eat this Oreo cookie and drink milk. Alright, so now let's go back to solving this problem. We want to find the heat of reaction. So let me add on to this. We want to find the delta H for this reaction. What is the heat of reaction? Or enthalpy of the reaction here? Well, we're going to need something. We're going to need that table that has all the standard heats of formation of all the substances. Alright, here it is. So, there are three substances, CO2, O2, and, oh shoot. Well, I just realized there's a typo, and I'm 10 minutes into this, so I'm not going to go back and fix it. I'll just address it right now. The original reaction was supposed to be CO plus O2. So I'm just going to pretend like that's what I had said in the beginning. Alright, so, like I said in the beginning, you had CO plus O2 yields CO2. Well, if we want to find the delta H and we're not doing it Hess law style, if we're going to use the standard heats of formation, Well, then I need to know the standard heats of formation of each of those substances. So we'll look for it on the list. And as we go down the list, okay, here is CO2. The standard heat of formation to form 1 mole of CO2 is negative 393.5. And here is CO. The standard heat of formation is negative 110.5. And let's look for O2. This is me pretending to look for O2. Okay, well, it turns out that that's not on the list. Yet, it doesn't have to be. It doesn't matter because, well, we have to think about it. Can anyone figure out why we are not given the standard heat of formation of O2 gas? Well, we need to remember the definition. It is the amount of energy it takes, or the heat change, the enthalpy change, to form a substance from its elemental components in their elemental state. Well, the substance is O2, oxygen. What elements make it up? Oxygen. And in its elemental state it's diatomic, and it's a gas. So the question is, what is the standard heat of formation of O2? What is the energy change required to go from O2 gas to O2 gas? Very good, you guessed it. Nothing. It turns out that all elements in their elemental state have a standard heat of formation of 0 because there's no enthalpy change for it to remain the same. So it turns out that we know it as well. It's 0. So as I had said from the very beginning of this video, 2CO plus O2 yields 2CO2. We want to find the heat of formation, the heat of this reaction. Well, you've got to remember that it's products minus reactants. So it's going to be this first, all the products minus all the reactants. So just put a P here and an R here. So the heat of the reaction here is going to be products minus reactants. So if you remember from this page, it is going to be the coefficient times the standard heat of formation. So let's take a look. If we're doing products minus reactants, then delta H of the reaction is going to be, we've got to do the products first, 2, that's the number of moles, times the standard heat of formation of carbon dioxide, and because that's all our products, we'll close that off, minus, and then we have to do our reactants. We'll start with the first substance. The coefficient is 2 times the standard heat of formation of CO, and then we add up the value for the other reactants that are present. So we're going to put plus, and the coefficient is 1 times the standard heat of formation of oxygen. And because that's all our reactants, we're done. We close that off. Now in the table back here, over here, we got their values. So let's go ahead and plug them in. Alright, so if I replace the standard heat of formations with their values, carbon dioxide was negative 393.5 kilojoules per mole. Carbon monoxide was negative 110.5 kilojoules per mole. And we weren't given O2 on the table because it's assumed, or by definition, it's equal to 0 kilojoules per mole. Now, because our units for the numbers in front are moles, and the unit for delta H is kilojoules per mole, moles is going to be reduced, and ultimately our final answer is going to be in just kilojoules, not kilojoules per moles or anything. So now we just have to do the calculation. And when we do it, we get negative 566.0 kilojoules. And that is your final answer. So there's so many different ways that you can be assessed on this. I could give you from the very beginning just this correct reaction. For example, 2CO plus O2 yields 2CO2. I can give you the table with the standard heats of formation, and I can ask you, is this reaction endothermic or exothermic? And how much energy is being absorbed or released? Well, you've got to do all the work to find out that you get negative 566 kilojoules, which, since delta H is less than 0, meaning negative, that means that this reaction is an exothermic reaction. Now, sometimes you can know this from the very beginning. Sometimes it's not very obvious at all. But we could kind of know this from the very beginning because one of our reactants is O2, which means this is a combustion reactions, and all combustion reactions are exothermic. Alright, and so now your homework is going to be pretty short. It's literally just going to be this problem set, these 5 problems right here. I want you to go ahead and use this table and the standard heats of formation from these values to calculate delta H for all of them. Alright, so we're done with thermochemistry, and what that means is, moving forward, you can expect to go into the next chapter, which is chapter 12, gas laws, which means in your composition notebook you have to do vocab, which I will expect to see on Wednesday. That is 13 terms, and those 13 terms also come with 7 key equations, and those can be found on page 355. Enjoy.